your home utility systems and save some energy. Well, before we dive in, first this disclaimer. Please take it seriously. Please, please, please do not try any of this at home. I'm going to do some dangerous stuff involving electricity, high voltage electricity, so you have the risk of getting shocked or even electrocuted. Things with high temperatures, so the risk of getting burned, and possibly toxic fumes, which may get you poisoned. So please do not try any of these stunts at home. All right, now let's dive in. I'll be having 4 stories for you today. How I regained my ability to breathe, how I got into an argument with my wife, how I'm planning to drive a Tesla for free, and how I ripped my motorcycle pants. And you might be thinking, how are these stories connected? Well, we'll know in a bit. But first, the ability to breathe. We all were a victim of the COVID-19 pandemic. We had to wear these face masks, which could be quite irritating, to properly breathe. That in turn gave a lot of attention to air quality. How well is the air that we breathe? How healthy is it, or how unhealthy is it? And also in my house, I had some small problems. So to illustrate, I brought this cross section of my house, and several rooms inside my house, I had several issues with the air. For example, in the kitchen, you would do some cooking, there would be steam in the air, and that's not very, very nice. You want to have some nice ventilation. In the bathroom, if I would be taking a hot shower, there's a lot of vapor in the air, a lot of moisture in the air that fogs up the mirror, and it's also not very nice to breathe all this humidity. And of course, the last one, the toilet. Well, we all know what happens in a toilet that's unpleasant for your breathing, right? So these blue lines are all the ventilation air ducts inside my house. And the toilet, the kitchen, and the bathroom are all connected to this fan in the attic. And that fan sucks all the air out of the house and blows it, over the roof to the outside, thereby drawing fresh air from the outside into the house, having some fresh air. So in principle, that was all well. So this is the fan that actually sucks out all this air, but it didn't work properly. I couldn't set it. So it has 3 modes: a nice quiet mode, 1 mode for a bit more ventilation, and then a 3rd mode, which is actually kind of hurricane mode, full power. But the only problem was, when I bought this house, this connector was not connected properly. So it had only 1 mode, which is the lowest one. So I didn't have very healthy air in my house. So when I looked at this plug, it is a Perilex plug, that's what we call it, at least in the Netherlands, and it has 5 pins. And the schematics are here, so the middle one is for safety, the earth, then there's 1 pin for the ground, and then the other 3 pins are the live wires, and depending on which of the 3 pins actually gets power, it determines the mode that the fan is on. So either the slowest one, the middle one, or the hurricane mode. So that got me thinking, well, if it's not hooked up correctly and it only works on the lowest mode, I want it to be functional, and it does so by putting power on one of these pins or not putting power on one of these pins. Maybe I can build something to control this. So what I did was grab a Raspberry Pi, bought a small set of relays, which is just a few euros, and by that device and hooking them up correctly, you can actually put power on one of these lines or disconnect power. So how it works is, in this picture there are 4 relays, these blue boxes, and depending on the mode, they send power from the middle terminal to either the left or to the right terminal. And the other one is disconnected. Well, you see some LEDs here at the top, which are labeled 0, 1, 2, and 3, which indicate the mode of ventilation, so I can turn it off completely or into mode 1, into mode 2, or mode 3. And there's sort of a rest position, so power goes to the right if the relay has no power, and if the relay receives power, the power goes to the left. What that enables me to do is, with this code, which is in Python, very easy, RPi GPIO, general purpose input-output, you can do some setup, like set the mode, because these top wires here are connected to my Raspberry Pi. And then I can set the input or the output mode of certain wires. And when this is a bit confusing, if you set the output to high, it turns the relay off. And if you set the output to low, it turns the relay on. So this way I can control which pin of my ventilation box receives power or doesn't receive power. So that was step number 1. That actually worked, but this is really tricky. You know, if you disconnect or connect these wires the wrong way, or forget to pull out the plug out of the wall, you might get shocked, and that's a bad thing. If you put power on the wrong pins, you might damage your device, so this is quite critical, so please don't do this at home. Then I built some nice code to build an actual controller, because this hardware piece enabled me to actually control the fan, but then, of course, where's the logic? Well, I made some nice classes, did some nice setup to designate, you know, which pin is for which mode, and then at the startup, I'm going to mode 1, the least amount of ventilation, because that's kind of the default. Then made some functions to either turn the ventilation off or switch to a different mode. Off is the easiest, just disconnect all power and we're done. And for the other modes, I did put some asserts in here just to make sure that I first disconnect certain lines of power and only then connect power to different lines again. Because I don't want power on all lines at the same time, because that might damage my device. So I got this nice controller, mode 1, 2, 3, and 4, and some other stuff, and that worked. I even built a nice UI, so I could control this from my phone, for example. As you can see, I'm not a front-end developer, but I took great pride in this UI. At least, you know, it worked. So it showed the current mode, and these buttons simply switched the controller to a different mode. So that was all fun and games. It all worked. That was nice. How it looked like this, because I wanted to take it one step further. With this UI, I still had to manually change the modes, which I didn't like. I wanted to do it automatically. And actually, I have a background in data science. So I was thinking, okay, if I take this wire, and on the inside of the wire, I have it connected to a humidity sensor, I can build a model to switch the modes automatically, you know, based on the humidity in my house. If it's rapidly increasing, I need more ventilation. And if humidity is slowly decreasing, I can switch to a lower mode of ventilation. One pro tip, there are multiple sensors. This is not the cheapest one, it's the second cheapest, because the cheapest one only measures by a whole degree of Celsius, which is not very accurate. And it fluctuates a lot. And it breaks down after a couple of weeks. This one is still my first one, and it's running for multiple years now without problems, and it measures to 1 decimal accuracy. It still has a dip or a peak from time to time, but overall it's quite okay. So if you want to do this, take this sensor or an even better one. The code for this is quite simple. There's some library that works only in Python 2, which just allows you to read the temperature and humidity. So you specify the pin that this sensor is connected to, and then you get a humidity and a temperature. That's it. So I do that every second to get a reading. And then I made this controller where I read the sensor every minute, and depending on humidity and temperature, because sometimes there's a peak or a dip, you know, below 0% humidity or above 100%, which doesn't make sense. So those measurements I disregard, and all the other measurements I just send them to a database, and just do that every 1 or 2 seconds. Once you have a database with all your data, it's very easy to build a dashboard. So I created this Grafana dashboard to display this visual information. And as you can see, the top one is humidity, the bottom one is temperature. It often still has some spikes, either down or up. Mostly are down, but sometimes also up. And when I showed this to my wife, was the moment when we got into a little argument. Because I wanted to use this to automate my ventilation system. And I could clearly see here's 2 peaks in the morning when humidity went up. First here, when I took a shower, and there, when my wife took a shower. And I started to make this thing automatic, but it wasn't very successful in the start. Why? I started with fixed thresholds. Just take a fixed value of the humidity, and if I cross that value, I want to ramp up the ventilation, and if I go below that value, I go to a slower mode of ventilation. So it's very simple. However, it's not accurate enough. Well, why? On the left, there's a picture in wintertime. On the right, in the springtime. In the winter, there's a relative high humidity, and in the spring, it's quite low. So, for example, if I would fix my threshold to 70%, it would work fine in winter, but it would never turn on in spring. Vice versa, if I would set the threshold at like 50%, it would work fine in spring, but never turn on in the winter. So when I built this in wintertime, at first it worked perfect. But then as we moved into spring, my wife started complaining because, you know, the ventilation did turn on when it didn't have to, and it didn't turn on when it should. So I was trying to make it better, and slowly but surely I got into this insight. Another problem was data cleaning. So the top one is the raw data, where we see these spikes all the time. So if I would have a sudden spike going either down or up, above or below the threshold, my controller would respond to it. It would switch to a different mode, which was not my intention, because I wanted to be, you know, smooth. Humidity doesn't change that rapidly over time. So in the second, in the lowest graph, I made some data smoothing. I just took the moving average. First, I used InfluxDB, and it has a very nice function, moving average, and it does exactly this for you, which is quite easy. But I also had to build this into my controller, which involved a little more coding, but eventually I got it to work. So I got this nice smooth graph, and it became a little bit more accurate. But then, of course, still I have this winter and spring and summer problem. So what I then did, because I just told you I have a background in data science, I built a classification model, an artificial intelligence machine learning model, which I would annotate some data saying, okay, in this period I had the shower turn on, which is the moment when I want to have more ventilation, or this is the time when I was cooking, I want more ventilation. And I would build this classification model. And it's quite easy to do so, because, you know, I have just a few variables. It worked quite fine. It worked a bit better than the fixed thresholds. But then, so first, you know, I regained my ability to breathe, because essentially, you know, this thing worked. When I would turn on the shower, ventilation would go up, the air would clear up, and I would be able to breathe nicely. But then a new problem occurred, because this thing popped up. Just like my wife, she's a princess. What is the actual problem? When I would turn this thing on, it's a water heater. It would create a lot of steam. The humidity sensor is so sensitive that it would pick up this steam and would immediately go into mode hurricane. So just by making a cup of tea, the whole house went into mode hurricane, which isn't very nice. And of course, the other princess was also complaining about this. So that got me thinking, should I change my model? Because, you know, it should be able to detect the difference between a shower or a water heater, but I failed. It didn't work. So it got me thinking, actually, I am missing some information. Because when I am in the shower, I am using hot water, while if this thing is on, I'm using electrical power. So maybe that's something I can do to add more information to my model or to my controller. But the wife wasn't satisfied. We got into this argument. She saw the dashboards, and we started blaming each other. You take the longest shower. No, you take the longest shower. So we kind of blaming each other, and I said, well, just don't turn on the water heater and drink water instead of tea. She said, well, no, I want my cup of tea. So I wanted to resolve this argument. You know, I didn't want to give in. So one day I looked at my water heater, which is responsible for the central heating of my house, but also providing hot tap water. And this blue display showed a lot of information, a lot of technical information about this device. So what I did was open it up. Please don't do this at home. This might be boiling hot, so you might get burnt. And if it's not set up properly, it might contain toxic fumes, which might get you poisoned. So please don't do this at home. I continued anyway, and I saw this circuit board, and then I was thinking, okay, how can I tap into this thing, hack into this thing? And then one thing caught my eye, which is, down here it says RS232. Well, some of you may already know what this is. It's a serial interface. And how it works, in the bottom here, if the voltage on one of these pins is low, below zero, or high, above zero, above a certain threshold, it indicates, it says here, a 0 or a 1. And that way, by flipping this voltage all the time, real quickly, we can designate a bit, either 1 or 0, and compose it into a byte. And that way, we can transfer bytes back and forth between the sender and the receiver. The Raspberry Pi supports TTL UART, which is here in the middle. It's kind of similar to RS232, except that low voltage is at 0 instead of below 0, but just a small technical detail. It does still work. So you can connect this to the standard serial interface of a Raspberry Pi and do the magic. So that's what I did. This interface also takes some fiddling to get it to work, because in this picture we have two devices that can communicate to each other, and of course the ground wire is connected to the ground wire at the bottom, and then RX and TX means receive or transmit, and then of course the transmit of the one device has to be connected to the receive of the other one, and then crossing for the other end, the transmitting of the one device to the receive of the other. But it's quite hard to get these designations from this circuit board and also to get them right on the Raspberry Pi. So it takes some fiddling around. You also have to configure this connection to read the data properly. But eventually I got it to work. It looked a bit like this. And the plug that was used is the same on traditional home telephones or office telephones. So this gray wire here was coming in from the central heating device into this thing, which is also commonly used in telephones, so I had it laying around. And I could connect these wires to the Raspberry Pi to the built-in serial interface. And that way I established the communication between my Raspberry Pi on one end and my central heating system on the other end. But in principle I had the communication, but I didn't know, I could read the bits and the bytes, but I didn't know yet what they meant. So that was the next problem. How to solve it? Well, I got a little bit lucky because the manufacturer of this system, this central heating system, provides this software free to use, although it is closed source, but it is free to use, and you can use it to read all the data from the central heating system. Even the mechanics of that company use this same software. So with this software, I could read the actual data of my device, but I didn't want to use it through this software in Windows. I wanted to have my own controller on the Raspberry Pi. But remember, the diagram with the read and the transmit, you can do multiple, let's say, attacks. You can do sort of a man-in-the-middle attack, literally, just connect the wires and see which bits are being transferred back and forth. But with this software of the manufacturer that I got, I could actually sort of reverse engineer what the reply was from the device and what it actually meant. Because I could sort of mock a reply and then see in this software which line would change or which value would change. So that way you can reverse engineer the entire request and reply between this software and the heating system. So if you do that, of course, I had some help from people on the internet. I had this script made, also in Python. You build just a standard serial interface to read from the serial device. You need to get these details correct, which is a bit trial and error, but eventually you will get it. Then it turns out you need to send a specific request, this thing, to the central heating system, which tells the system, I want to know your current status, all your current details. So first you have to send that part of information, then you wait for the reply of the device, because it takes a little bit of time, a couple of milliseconds probably. Then I'm going to parse all that response, and then I get all this information. It is in Dutch, but you'll probably get some, for example, the pump, whether the pump is running or not, Legionella for safety, anti-Legionella for health, the set point, the temperature set point, for example, on the thermostat in the living room, water pressure, and all this interesting information. So as a data scientist, that got me excited, like, oh, I have this treasure trove of information. Let's do some stuff. Of course, save it to a database, that's step number one. That also enabled me to move to a rule-based model for my ventilation. First, I had a classification model, but it failed due to the water boiler. But now I actually know whether somebody is in the shower, yes or no. Because from my central heating system, I know whether hot water is requested through the tap, yes or no. And even by how much. So if I would open the tap in the kitchen, it would say like 3 liters per minute, while a shower would take about 6-7 liters a minute. So I could even designate between hot water in the kitchen or hot water in the shower. So I could change my rules just a little bit with this additional information to make the controller more accurate. Well, the plus side, it is still deterministic. It is quite simple. It's just a few lines of code to actually write this rules. The only problem was it requires some trial and error. So eventually I got it right to get the exact values right. Wife was happy, I was happy, life was great again. How did these rules look like? Quite simple. If I am currently in mode 1, so the lowest mode of ventilation, and if the derivative of the humidity is positive, which means that the humidity is increasing, and if the second derivative of the humidity is also positive, which means that the humidity is increasing but at an increasing rate, so it's going up faster and faster, that means I'm in dire need of more ventilation. So I will move to mode number 2. Else, if I was already in mode number 2, and humidity is still, the first and second derivative is still positive, and hot water is being requested, so the water, I'm actually in the shower or in the kitchen, then I want to move up. On the other hand, if humidity is quite stable, that means I have sufficient ventilation and I can move one step down in my ventilation. Well, the same for mode number 3. If humidity is decreasing at a rapid rate, I can also move to a slower mode of ventilation. And if it's fairly stable, I can try to move one mode down. If I do move down, but then humidity increases again, then the other rule will trigger and it will move back up to mode number 3. So perfect, I got this resolved. I could take a shower and ventilation would change up and down automatically. No more need for the mobile app, which was great. And I also looked at this dashboard because I still had the argument with the wife unresolved. Who takes the longest showers? Remember? So this is the raw humidity, and we clearly see 2 bumps. The first one was from my shower, the second one was the wife. Here we see the ventilation controller, which mode it is in. So when I started, it moved to mode number 3 straight away. Then after some time back to 2, and after some time back to mode number 1. And then the wife took the shower, again straight back up to 3, back to 2 for a little longer, and then back to 0. So that got me excited to actually win the argument. This graph said, for how long has hot water been requested from the central heating system? And these are the two graphs. And I couldn't tell which one was bigger than the other. So I thought they were quite equal. So I was actually being honest. I told my wife, okay, this is the result. We take an equal amount of time in the shower. Happy wife, happy life. So that issue got resolved. And I even got a little bonus. In the summer, it gets quite hot in the Netherlands, not quite as hot as in Spain, but still it can get quite hot. I had this little bonus rule because my central heating system is connected to the thermostat in the living room. And that temperature sensor in the living room is very, very accurate. So whenever the living room has a high temperature, I just scrape some data from the public Institute for Weather in the Netherlands. I just picked a nearby weather station. If the inside temperature is above 22 degrees and the outside temperature is below that temperature, then I am also going to increase my ventilation a bit to try to cool my house. Because if I increase the ventilation, the hot air from the inside is blown to the outside, and the cool air from the outside is drawn into the house. So that way I can actually cool my house a little bit in the night to have a cooler house during the day in hot summers. So that was even a nice bonus. Now my wife was actually convinced, okay, you got a pretty nice system here. I love it. Third story. I was busy with this electronics, all these electronic devices. And I was thinking, well, how could I drive a Tesla for free? You know, who wouldn't want to drive a Tesla, let alone for free? So I started planning. First, I got up to my roof. This is actually my roof. And these 8 solar panels, I put them there. I just invited some friends over, lifted all this stuff up, mounted it, treated them with some beers, and I had this solar installation on my roof. Generating power, it works nice, because my bill from last year actually kind of cancelled all the high energy prices, so I was quite happy. On the inside, you have a device like this, an inverter, because the solar panels provide DC power, but your house and your wall sockets have AC power. And this device converts from DC to AC. This is a grow-out device, and it also has an interface to connect. You could use the app from the manufacturer, but that sends the data to the manufacturer, and you're limited by what they offer. So I only got some data like once an hour, and an aggregate of the last month, and that was all. But I wanted more. So I looked at the connections on the bottom of this inverter, and I found this serial connector, RS485. It is similar to the one that we used before, 232, but this one is a little bit better. Instead of 3 wires, I only need 2 wires, and you could connect some more devices. Well, I have just 2 devices, the Pi and the inverter, but this thing is a little bit better, has a bit more capabilities. Unfortunately, the Raspberry Pi cannot, out of the box, read this protocol so easily. But you can buy this USB converter, just a few euros. I stuck it in there and was able to connect to my solar inverter. Code is quite simple. You need a package Pi Modbus to connect with an RS485 device. Again, you need this details about these values. You need to get them right. Turned out that the documentation of Growatt has most of this information, but Growatt is a Chinese company, and I think the documentation was automatically translated, so a lot of information was lost in translation, but just studying trial and error, you'll eventually get these values right. So I got my Pi connected to the inverter, and I can actually read data. You can read what they call registers, the input registers. And if there's no error, I can build a very large dictionary with a lot of details, like the status, how much power is being put in from the solar panels into the inverter, how much power the inverter is putting out, so providing to my house or to the electricity grid, the frequency, the voltage, well, you name it, it's in here. A lot of information. So I write that to a database will write to get this information every second or two. You can even read some configuration. You can even change the configuration by writing back to these registers. So I could change like LCD language. Well, I don't think that's very harmful, but all the other stuff is, you know, a little bit more dangerous. So I didn't touch any of those because I didn't want to damage my brand new inverter. So with this in place, I can actually read all that data every second or so, and that got me this graph, which got me very pleased because the inverter has a maximum power capacity of 3000 watts. And we'll see here the peak in the afternoon is around 3000. So that functioned correctly. And this is kind of a, you know, average graph on an average day. In the morning, power generation starts up, peaks at noon, and then drops down gradually. The line wiggles a bit for, you know, some clouds here and there, or some birds flying over, I don't know. So this also worked, and I also got this information. So that was very nice. Because I could also use it to optimize the inverter even more. Because I had all this data, and that got me thinking, how can I optimize this device even more with all this information? Well, it turns out that this device gets very hot. Because for the conversion, it also consumes some power. And you'll see some metal fins here in a row, and they are for the cooling. And the highest temperature I've seen is around 70 degrees Celsius at, you know, peak power. So that's quite a lot. It's quite hot. And electricity tends to be less efficient if temperature goes up. And this thing also tells me what its temperature actually is. So what I did is took this fan from a very old computer, stuck it underneath, and built a very simple controller to optimize the inverter. So whenever the temperature is above 40 degrees Celsius, then, similar to the controller I built before for the fan, I turn on this fan to cool the inverter, and I'll leave it on for at least 10 minutes, because this temperature changes quite slowly, because it's a big block of aluminum. It holds a lot of temperature, it holds a lot of energy. And I also don't want the fan to turn on, turn off every couple of seconds. And then if temperature drops again below 35, then I'll turn the fan off. So it's a fan consumes very, very little power, and I get that back with increased efficiency of the inverter. And it works really well, because I got these averages. This is data from last summer, some nice summer days. And this shows the amount of power that was generated on that day. So on a good summer day, I think this is not totally my record, but close to the record, 21.7 kilowatt hours in just one day. So that got me excited, like, okay, I have all this power, literally. How can I use this power to my own benefit? And it got me thinking, well, on average, I consume only about 7 kilowatt hours per day. So I have 13 kilowatt hours of electricity, you know, on an average summer day, left over. And I just send it back to the grid, and you get some money back, but it's only a few cents per kilowatt hour, so you won't get rich. But it got me thinking, can I do something else with this power? Well, if you would buy a Tesla, you would receive this wall charger for free, which you can just plug into the wall socket and the other end into the car. And with 13 kilowatt hours, I can get approximately 80 kilometers of range. Well, on an average trip to work and back home, this got me covered. So I was thinking, okay, nice. If I have this in place, I can drive a Tesla for free. Only part I didn't figure out yet is when you order a Tesla, you actually have to pay for the car. So I'm still working on that part. Well, once I have it though, I'm going to be driving for free. All right, last story. How I ripped my motorcycle pants. From the inverter, I got all the data. Every second, I know how much power is being generated by my solar panels. But I didn't know how much power I was actually consuming myself and how much I was providing back to the grid. To get that information, I tapped into this device, the electricity meter, and I know it differs a bit per country, but in the Netherlands, all these utility devices are inside the house, generally in a very small room right next to the front door. And this black device handles all the electricity. And notice there's a very small cable here, the black cable, because this is a socket with RS232. And I did that before. So I put a very small laptop here at the bottom, an Asus one with an Intel Atom processor. So I think it's even worse in performance compared to a modern day Raspberry Pi. But hey, it worked. It didn't have a serial connection though, which the Pi does. So you need to buy one of these things, just a few euros, very, very cheap. You stick it into the USB port and the other end is just a serial interface. I got that connected. And of course, this protocol is a little bit different. Let me scroll back up. It's a little bit different to parse the data. Oh, and actually also a funny thing, the device end would call itself USB 0 by default, but every now and then it would flip to USB 1. Then after a couple of days, it would flip back to 0. So I built this small function that, once I lose connection, I try the other one for as long as it works, and as soon as that stops, I try to switch back. So again, you need to have this configuration right, which you can get from documentation of the electricity meter. And then every second, I read all this information. Well, to get this right, just dig through the documentation. I can get the low tariff power that I consumed, the high tariff power that I consumed, and also the power that I produced. If I produce more power than I consume by my solar panels, I'm producing back to the grid. So I can get all this information, which I also put into my database, and of course into my dashboard. So I got this. The blue line is what my solar panels generate, and then we have the green and the yellow. One of the two is positive, and the other one is 0 at any time, because the green one is positive if I consume power from the grid, and when I'm providing back to the grid, green is 0 and the yellow becomes positive. And then yellow indicates how much power I'm giving back to the grid. And as you can see here, I'm having a lot of power because the blue one is high, but I'm giving it all away because the yellow one is also high. So if I cancel these two out, I can calculate the actual amount of power that I'm consuming myself. And that got my wife thinking, well, if we have all this power and you want to put it in your car, I can also use it. Well, you have to know she likes to bake cupcakes, pies, these nice drip cakes, everything. And I volunteer to eat them. And I'm quite slim, but after eating a lot of cakes, you kind of gain some weight. My motorcycle pants in the Netherlands, it's a bit more dangerous to drive a motorcycle, so it's full leather. And the pants is actually, it's meant to be quite tight. So after eating all these cakes, I had to put on the pants and zip up. And I would kind of walk over to my motorcycle, because I couldn't really move anymore. And I tried to step on, and it ripped a hole all over my ass. So that's how I tried to improve my house, but instead I ripped my pants. Thank you to Codemotion for having me. Audio Visio, thank you for attending.